Let's talk about our prime factorization. And here's where we need to know our primes and our composites. Every composite number, so a number that has more than two factors, can be rewritten as the product of prime numbers. I made a mistake there, so I had to redo it. The product of prime numbers. That means prime numbers that are multiplied together. Basically, we're trying to break down a number into its more basic components. Now, we don't normally just do this like in normal life, but in higher level math, we do use prime factorization a lot when we're working with bigger numbers and we're trying to find what they have in common. And we actually break them down using prime factorization to see what they have in common. So it's actually a very useful thing. So an example, the prime factorization, I usually abbreviate it as PF, of 60 is 2 times 2 times 3 times 5. This is the prime factorization. We broke 60 up into numbers that are multiplied together, and all of those numbers are prime numbers. 2, 2, 3, and 5 are all primes. Now, another way of listing this out, whenever we have repeated numbers, we like to write them using exponents. So 2 times 2, I'm going to say 2 to the second power. I have 2 2s, times 3 times 5. Now, does 2 times 2 times 3 times 5 equal 60? It does. 2 times 2 is 4. 4 times 3 is 12. 12 times 5 is 60. So these numbers multiply to get 60. This is just another way of showing 60. Now, how do we do this? We usually use a factor tree. A factor tree to find our prime factorization. So how does this work? What do? We're going to use a factor tree. Hello, again. Once you use your factor tree, which I'll show you in a second, you are going to circle your prime numbers. This is a good thing to do because especially as the numbers get bigger, it's easy to lose things and you want to circle them so you don't just kind of flick some off into space and forget about them. Once you've broken everything down and there are no composite numbers left, just primes, you are going to list all of your prime numbers from smallest to biggest. We like to go in order and we like to stay organized. You are going to use exponents for any numbers that are repeated, okay? So for example, 5 times 5, well, that's repeated. I'm going to write 5 squared. 5 is the number that's repeated. And the number in the upper left-hand corner, your upper right-hand corner is your exponent. That's how many times it's repeated using multiplication. So 5 to the second power, or 5 squared, means I have 5 times 5 2 times. 5 times 5 is 25, not 10. Remember, we can usually make more than one factor tree for a number. In fact, I could take a number and make a factor tree. You could do the same one, and we would actually have different factor trees, but all factor trees for a number will end up with the same prime factorization. Every number has only one prime factorization if you do your math right. So there's lots of different factor trees you could do. You'll end up with the same prime factorization no matter what factor tree you do, which is kind of fun. At the end, you can check your work. Multiply your prime numbers to see if they equal the number that you started with. They should. Let's go ahead and do an example so you see how this works. Let's find the prime factorization of 63. Now I've done a little more organized one for you here. We're going to follow this rule. 63, I'm going to start breaking it up into its factors. Let's see. Just whatever factors stand out to you that might seem easiest. I broke them up into 9 times what gives us 63? 9 times 7. I take a look at 9 and 7, those are two factors, and I go, well, 7 is a prime number. I'm going to circle it. I take a look at 9. 9 is not prime. I need to continue breaking this one down. Let's see, what are two factors of 9? I don't want to do 1 and 9 because then I would still, number 1 isn't prime, and I would still have 9. That would be silly. Oh, 3 and 3. Oh, and I know that 3 and 3 are both prime, so I circle them. I don't have anything else to break down because here this tree ended with a prime, these trees ended with primes. I'm done breaking things down. Now I'm going to list them out in order. So 63 is going to be 3 times 3 times 7, or if you want to do the times thing, you could do a dot, 3 times 7. That means the same thing. Now, here's the next step. If you can do this, I know we haven't done with exponents a lot, but if you can, go for it. 3 is repeated, so I want to do this part right here. I want to rewrite this part using exponents. So 3 is what's repeated. How many 3's are repeated? 2. 3 to the second power, and then I don't want to forget about that 7. So 3 times 3 is 9. 9 times 7 is 63. Boom, we got it. Let's go ahead and make our own factor tree. Let's find the prime factorization of 52. Let's go ahead and do maybe a couple of them. Okay, 52. I'm going to break 52 down. The first one I thought it was actually 2 because 52 is even. So let's see, 2. 52 divided by 2 is 26. So I have 2 and 26. I'm going to take a look at those. Oh, 2 is prime, so I'm going to circle it. That's my only even prime number. 26 isn't prime, so I'm going to continue breaking that one down. 26. I think the only thing I can do is 2 and 13. So 2 times 13. I take a look at, 2 is prime, so I'm going to circle that one. And 13 is prime, so I'm going to circle that one. And, I am done with my factor tree because that branch is ended in a prime and these branches ended in a prime. I'm not done yet with my problem. I'm just done with my factor tree. Now, we're going to list the numbers in from ascending order. So I have 2, 2, and 13. So 2 times 13. That's my prime factorization. I'm going to do that extra step, and I'm going to write my repeated 2's as exponents. So here's my number that's repeated. How many of them do I have? I have 2 of them. And then I'm not going to forget about that 13. So this would be my final complete answer. This answer right here is correct, but this answer is more complete. Let's go ahead and do a different factor tree, and you're going to see how you end up with the same answer. So let's do 52, and this time I'm going to go, 52. Ooh, 52, that reminds me of cards. I know that there are 4 decks in a deck of 52 cards. So I'm going to break it up into 4, and there are 13 in there. So 4 and 13, I know are factors of 52 just because I like cards and I play solitaire a lot. Okay, 4 is not prime, so I'm not going to circle it. Oh, but 13 is prime. There we go. So I'm going to circle 13. That branch is done. I take 4 and then I'm going to break it down again into 2 and 2. Those are both prime. And wait a minute, 2, 2, and 13. So you see both are different factor trees, but you end up with the same prime factorization no matter what factor tree you use. So go ahead and practice doing a couple of prime factorization trees.